Hi everybody, welcome to another video in Business Calculus, section 12.4, the definite integral. In this section, we answer two important things about integral. The first one is what the integral is about, and the second is why do we use the notation for the integrals. So the first question, so if we say derivative is the slope of the tangent line, then the definite integral is the area under the curve. So let's look at the first example, approximating the areas under the curve. Y equal to 0.25 x squared plus 1 from x equal to 1 to x equal to 5. So I'm just going to make a table for x equal to 1 to x equal to 5. One, 2, 3, 4, and 5. So just put 1 in here and evaluate. That will be easy. I will use the calculator for that. Right, and then go to the table, second graph. Right, when x equal to 1, we have 1.25, 2, that will be 2, 3, 3.25, 4, will be 5, and 5, 7.25. Right, so we plot this point, 1, x equal to 0, y equal to 1, we also have the y-intercept there, right? 1.25, 2, 2, 3 and 3.25, 4 and 5, and 5, 7.25. You see, look like a parabola. It is a parabola. Right. So now we calculate the area under the curve for x equal to 1 to x equal to 5. So estimate this area here, area under the curve. And of course, we have to specify the lower bound, but the lower bound is the y-axis. So the area under the curve, but above the x-axis. I mean the axis y equal to 0. Right, to estimate this, we can just divide this into rectangles. Of course, the worst approximation is just say, okay, let's use that area to estimate it. And then we say that's not a good approximation because it is a curve. So we need one rectangle will not estimate it. So on this problem, we'll focus on the left end points, and there will be 4 rectangles. So with these 4 rectangles, meaning the interval from 1 to 5, we divide that into 4 equal segments from 1 to 5. And so 1, 2, 3, 4. And for each segment, we use the left end point. So this is the left end point. So for the first rectangle, we will have the width is from 1 to 2, and the height is whatever the function is at 1. So that is the first rectangle. The second rectangle is from 2 to 3. The second subinterval, we use the left end point, and we draw the height. And that is the second rectangle. Then the third rectangle from 3 to 4. Use the left point to find the height. And the last rectangle, the last subinterval, we use the left end point. From 4 to 5, we use the left point, which is 4, and we find the height based on that. So we have 4 rectangles, and now you see that if we estimate the area of those 4 rectangles, that will be close to the area under the curve. And we said that's close but not good enough. Well, if it's not enough, we'll make more and more rectangles. The more rectangles we have, the better the approximation is. Alright, so in that case, we just find the area of this rectangle. Alright, so from 1 to 5 divided to 4 equals segments. So we say the width of a rectangle from 1 to 5 and 4 rectangles. So the width is equal to 5 minus 1 divided by 4 equal pieces. So that gives us 1. So that's why the width is equal to 1. And then so we have the width is 1, so we go from 1 to 2, 2 to 3, 3 to 4, and 4 to 5. And for each subinterval, we use the left endpoint. So, and we just estimate the area under the curve. So we add the area of all of those rectangles. So the first rectangle is here. The width is 1. The height is based on the left endpoint, which is 1. We just say f of 1. And now we add the second. The width is 1. The height will be based on the left endpoint, so 2. The width is still 1. And then the height is 2. And then plus the width is still 1. The height from 3 to 4 we use the left endpoint, which is 3. And then the last one, the width is 1. The height is based on the left endpoint, which is f of 4. Right. So here we can say it. Of course, the width is 1. We really don't have it. So add all of this up. We just have f of 1 plus f of 2 plus f of 3 plus f of 4. And if we want to, all of that multiplied by the width equal to 1, which of course that's not necessary. Right, 1 is 1.25, and for x equal to 2 we have 2, 3.25, and 5. So add all of them up, we have the answer. 2 to 7 is 2 to 5 is 7, 1.25, 3.25, that's 4.5, so 11.1, 11.5. Right, 11.5. So that is the estimate the area under the curve using 4 rectangles from 1 to 5 and using the left endpoint. That's what we have. Right. Now of course we can use the calculator for this too. Remember we did enter y equal to y1 is that. Now all we need is y1. So alpha trace. Hit alpha trace, you see y1 there. Of course if we don't use y1 like that, we can hit variables, y variable, function y1. Either way we have y1. If we evaluate at 1, that's what we have. Right, but we need to evaluate at more than 1 point. So we'll use the set. Hit second, the parentheses. You see above the parentheses there the curly bracket. And in that case we can evaluate at this 4 point. Close the curly bracket, close the parentheses, and that's what we have. Now all we do is just add all of this up. Second stat, go to math, option number 5, and we just add everything we have. So go up there, highlight that, hit enter, that's it. 11.5, of course, times 1, which is still 11.5. Right, so that is where we use the left endpoint. Now if we use the right endpoint, first let me draw the curve again. So that is the curve again. Now we still have from 1 to 5. And we still divide to 4 rectangles, but this time it is the right endpoint. So we still have the width is still 1, right? 5 minus 1 over 4, so the width is still 1. So from 1 to 2, again we divide into 4 equal segments. From 1 to 5, so we have 1 to 2, 2 to 3, 3 to 4, and 4 to 5. Now, for the first interval of 1 to 2, we use the right endpoint, so that's why we have this rectangle. For the second rectangle, use the right endpoint of from 2 to 3, we use the right endpoint, which is 3, and based on that we find the height, and we make a rectangle. And then the next interval from 3 to 4, we use the right endpoint of that, draw the height. And last interval from 4 to 5, use the right endpoint, make the height, and have the rectangle. Okay. So we add the area of all those 4 rectangles. We have the area under the curve. Just an approximation. Right. So I'm just saying, for the first rectangle, the height will be based on the right endpoint, which is 2. Second rectangle, the width is 1. The height based on the right endpoint, which is 3. And the third interval from 3 to 4, the right endpoint will be 4. And then the last one, f of 5. Right, factor out the 1. And then we have f of 2, f of 3, f of 4, and f of 5. Right. Multiply by 1, of course, we don't really need that. So just f of 2, f of 3, 4, and 5. Right. And now let's do by hand first. F of 2 is 2. F of 3, 3.25. F of 4 is 5. F of 5, 7.25. 7.25. So 7 and 3.25, 7.25, that's 10 and a half, 17 and a half. Right. If we use a calculator, first, of course, y1 is still that function. Alpha trace y1. Now we will evaluate at 2, 3, 4, and 5. Close it. Right. Now second stat. Go to math, option number 5. And we'll just highlight, copy and paste. Or if we don't want to do that, we know the answer is this. We just hit second, and this key, we have the last answer on the calculator. Right, we have that. Right, all of this, of course, we multiply by the width is 1. Right, let's go to more theory. But sorry, before that, we see one of them is underestimate. One of them is overestimate. It doesn't matter. When we have the more rectangles, we have the better the approximation is. So the goal here is just increase the number of rectangle indefinitely. Right. Now, we have a theorem. If the function is positive, right? So we talk about area under the curve. If the function below the x-axis and we use the height, that could be negative. So the way we define this, well, we let the function be positive, either increasing or decreasing. Then we have the width is b minus a over n, and the absolute values of f of b minus f of a. So that is the area bound for the approximation of the area between the graph of f and x-axis from A to B. Right. So B minus A over N, that is the width of the rectangle. And it says that if the function is positive and either is increasing or decreasing, then the left and the right sum approach the same number as n go to infinity. So that is very important. So estimate the area under the curve. The more rectangles is, the better the approximation. So therefore, if we take the number of rectangles goes to infinity, the left sum and the right, the sum using the left endpoint and the sum using the right endpoint are the same. Because of that, we can just use either one of them. Right. Let's look at this example. Approximate the area in the curve y equal to e to the x from x equal to 1 to x equal to 3 using 5 rectangles and using the midpoints. Well, interesting. Right, we don't really need to sketch the graph. We know e to the x is going to be positive, which is good. By the way, exponential function going like that. So it is increasing. Right, what we do here is just draw an interval, most importantly from 1 to 3, right? Right, say 0, 1, 2, and 3. Right. So it's nice and all, but we can draw the graph, and because the graph is exponential, I'm just going to sketch just something like that. We know it's positive. Right. Most importantly, we focus on the x-axis. From 1 to 3, x equal to 1, x equal to 3, and divide to 5 rectangles. So first we calculate the width. Which we use delta x the sample for the width. Difference of the endpoints divided by the number of rectangles. So 3 minus 1 over 5, 2 over 5, 0.4. Right. So from 1 to 3, we divide to 5 equal segments. The width is 0.4. Right. So 5 segments, right? 1, 2, 3, and 4. Right. Make it easy to see. So right, 5 equal segment from 1 to 3, and the increment is 0.4. The width is 0.4. So we have 1. The next is 1.4, 1.6, 1.8. Sorry. The width is 0.4, so 1.4, 1.8, 2.2. Sorry. 4, 8, 2.2, 2.6, and 3. Right, so that 4 equal segment. Right, plus 0.4, plus 0.4, plus 0.4, and then so on. Now, for this one, we actually use the midpoint to find the height. So the midpoint, of course, for the first interval from 1 to 1.8, we use the midpoint, which is 1.6. And whatever the height is, we'll draw a rectangle for that. Next, between 1.8 and 2.2, sorry, this is the second rectangle. The first rectangle is from 1 to 1.4, right? So between 1 and 1.4, that's 1.2, and that's actually the first rectangle. And then between 1.8 and 2.2, that's 2, and we find the height for that based on 2, and then so on. So pretty much we use the midpoint 2 between 2.2 and 2.6, that's 2.4, 2.6 and 3, that's 2.8. So those are the midpoint, and we use the midpoint to find the height. So the estimate, the area will be the width of 0.4 times the first height is the midpoint from 1 to 1.4, which is 1.2. As you see, we don't even need what the function look like, just need to make sure that the function is positive, because we do find the area here. 1.6. 2. 2.4. I mean f of 2, f of 2.4, and f of 2.8. So we factor out 0.4. So f of 1.2 plus f of 1.6, f of 2, f of 2.4, and f of 2.8. Right, so that's easy enough. Now we just use the calculator. First, so we enter the function e to the x. That's easy. Right, that's good enough. E to the x. Right. Now we need y1. Evaluate at those values. So second parentheses to get the curly bracket 1.2, comma 1.6, comma 2, comma 2.4, comma 2.8. Close the curly bracket. And I just need to add all of this up. Second stat, sorry. Option number 5, and we add everything above. Right, that's what we have. But then again, we have to multiply by the width. 0.4 times, again, second, this button, we have the last answer. So 0.4 times that is 17.25. If we just estimate, that's what we have. Right, so that estimate area under the curve, we use the left endpoint, right endpoint, and of course the midpoint as well. The width is the difference of the endpoint divided by the difference of the interval divided by the number of rectangles. That's what we have. Right, so now we define the definite integral. Right, so let f be a function defined on the interval. We define, we partition or divide the interval from b, a to b into n rectangles. So this is the width, as we mentioned before. And the endpoint, like that. Then we can use the left endpoint, the right endpoint, and the midpoint, or any point in between. So the Riemann sum in general, we can use any point between each subinterval. So between 1 and 1.4, we can choose like 1.3, and then 1.4 to 1.8, we can choose 1.45. And any point in the middle would be fine, because the idea here is we take the number of rectangles goes to infinity, so the width of the rectangles will get smaller and smaller. Eventually, it's too close. It is too close, then we just pick any point between the interval will be correct. So in that case, in general, we can just pick any point in the interval, and then we multiply by the width. And with that, we arrive in this notation. The summation from 1 to n, meaning we have the area of the first and to the last rectangles, the width times height, right? So that's exactly what we do, but with the more systematic formula. right? Now, so that is the sum of all the rectangles. Now take that to the next level. Now, we did say that the more rectangles is the better the approximation. So what if we take the limit of rectangles go to infinity? Well, if that is the case, what we have is the definite integral. It is definite when we have the limit from a to b. This is the area under the curve from a to b, if we're talking about positive function. Now, the definite integral is no longer area, because that could be negative. The function could be negative. As you see here, f does not need to be negative. It doesn't have to be positive. So it could be anything. So the integral could be positive, could be negative. But the definite here, the definite integral is that we have the limits of the function. Right. Now, if we're going to write this is the limit of the Riemann sum, so we say that is the limit as the number of rectangles goes to infinity, the summation right. We just take the number of rectangles go to infinity, and we have that. And now the notation, the first question, the notation for integral. Why do we, remember, indefinite integral is where we don't have the limit. Definite integral is where we have the limit from a to b. Right? Now, why do we use the notation like that? Well, this looks like an S, and in fact it is elongated S, which stands for the summation. We have the function, we give us the height, the delta x give us the width. So that's exactly the notation of integral, right? The integral sign for the summation sign, the function is the height, dx or delta x is the width. So we just have exactly area under the curve if the function is positive. If the function is negative, well, that's no longer area. Right, here we have some properties of definite integral. Now, once again, loosely speaking, I'm just going to say the area under the curve. But if the function is negative, the area cannot be negative, so that is a problem. So in fact, we define this integral calculate the net area, meaning that if the function is negative, that could be negative as well. Great. So definite integral from a to a, this will be equal to 0, because if we have, let's say, the function going like this, and there's a and f of x is the function. So from a to a, we just have one vertical line. Of course, a vertical line has no area, or any line has no area. Right. The next part is if we interchange the limit a to b, b to a, we throw the negative. So we interchange the limit, we change the sign of the integral. And now this property inherited from the indefinite integral. We can take the constant outside, plus and minus in the middle, be plus or minus in the middle. So that's exactly as limit derivative integral, because after all, we do have the limit like this, so the constant, again, we can bring it outside. So these properties are just standard properties of limits integral derivatives. And then now this is new. If the limits are the same, that will be 0 because there's no width. And if we interchange the limit, the integral, we change the sign. Right, next, from a to b is equal to a to c and to c to b. And the nice thing about this is c doesn't have to be in between a and b. C need not, doesn't need to be in between A and B. So essentially we can go from A to C and then go back to B. that's still the same as go for directly from A to B, right? So if we want to go from A to B, that's the same as from A to C and then back to B, as long as so in that case from A to B we can just split. And notice that this is called the way we say this is the integral or the definite integral. Usually when we say the limit, we know that is definite integral. The integral of f of x from A to B. It always written from bottom to the top. So this from A to C and then from C to B is the same as from A to B. Right, let's look at some simple example of that. Now if we have the definite integral of fx from 0 to 3 is 5 and from 2 to 3 is 2. Again, we don't know what the function is. That's what we have. So first, what is this? Well, what we notice here is that this is just that one, but with the limit interchange. So if we interchange the limit, we throw in the negative. And without the negative, it is 2. So with the negative, it is negative 2. Simple enough. Next, the integral from 2 to 2. Well, 2 to 2, the limit are the same. The width is equal to 0. And the arrow will be 0 because we have no width. So if we have the same limit, the integral will be equal to 0. I still on that problem. Find the integral from 0 to 2. Well, what we have here is from 0 to 3 and then from 2 to 3. We don't have from 0 to 2. Right. So in that case, we have 0, 2, and 3. So those are 3 points. Now, if we don't want to go from 0 to 2 directly, we can go from 0 to 3 first and then from 3 to 2. So I will split the integral as follows. We still go from 0 to 2. And then we can go from 0 to any number, 0 to 5 and then from 5 to 2. That's fine. But this problem we have 3. So we better use that. So we can go from 0 to 3 and then from 3 to 2. That's what we have. Now, from 3 to 2 we actually have negative 2 already. But if we want to, we just interchange the limit and throw in the negative sign. So from 0 to 3 the integral is 5. And from 2 to 3 the integral is 2, but there's a negative. Two. So that gives us 3. 5 minus 2 is 3. Right. And the next we have the properties which inherited from like that limit. And then so limit, derivative, and integral, summation, all of them have these properties. So first there's a plus in the middle. Why don't we split? Into so just a reminder, I mentioned this in the previous section, the integral and the dx goes together like the quotation mark. You cannot have one without the other. The integral is to denote that and open the notation, and the dx is the close of that. Right, so we split into two integrals, of course, 2 dx. Then the 3, we talk about that, we can bring it outside. Right now we just look at the problem. From 0 to 5, the integral is equal to 10. And from 0 to 5, the integral of g of x is equal to 5. So you have 10 plus 3 times 5. That's 15 and 10, that's 25. Right, so that's just some properties of definite integral. Right, to recap, in this section, we learned about definite integral, which is the limit of the Riemann sum. And the Riemann sum estimates the area under the curve if the function is positive. By the way, as you see here, the way we define it, the function doesn't have to be positive. So the Riemann sum doesn't just calculate area. Like I said, if the function is negative, we cannot just have area. So we have that. And take the limit as n go to infinity, we have definite integral. And we should see there's the relation between the integral sign and the summation. The function is the height, dx is delta x. So there's a connection of those concepts. And if the function is positive, we calculate the area under the curve. And here's some properties of the definite integral. These two properties are properties of integral. Now just have the limits. All right. So with that, I stop here for section 12.4. As always, thank you for watching and see you in another video in business calculus.